Okay, recording is on. Well, first I've looked to Aula Web. Aula Web is here. Oh, okay. Can you see my shared screen? Is the Aula Web page?
Yes, we are on the Aula Web page.
Okay. Just to look what is inside in this week. First I have here there is the basic shell commands. Basic shell commands is the new version with respect to the previous document. Unfortunately, I have to publish the new versions without erasing the previous ones, because the AMA note, that is the tool for for writing on the slides and so on, requires that you never delete a previous document. Otherwise, all notes are lost. So this is the 1.1 version with enhanced list of commands. I posted in my long video tutorial on how to use the shell. Another document that is shell programming. Shell programming is not a part of our course program, so nobody will ask you this skill at the exam. But I think that some of you may be interested in. Sorry. Shell is a real powerful programming language, a script language, and is much used by system programmers, in particular for deploying software, for automatic installation, for porting software through different machines and so on. So it's old version or philosophy on what now is can be done with other deployment systems, but is absolutely useful. And Shell is a real programming language inspired to C. And here there is a link to, you can find books and documents on shell programming. Yeah, please. Okay, you can find in the network, in internet, many documents of this kind. I just posted a link to short document that I find really rational and simple. So if some of you is interested in, do it at your own risk. So I'm not responsible about what happens of the effect. Well, yesterday we had a class exercise with the solution. So I assume that you have done it and you have watched it, the solution, and learned how it works. So starting from this class, we will have more complex exercises, and in particular here, Wednesday class is a directory with the new exercise that we will start working on in half an hour or something like that, or next hour. And this is a wrong document. This is the original form instead of the PDF, so we change before you use it. The name P6 has nothing to do with sex, it's exercises. So as an examples. So there are slides with example that you can read. You must read, understand, and you can also use, copy and paste, and compile and run, and use part of the examples to compose your new exercises. Some of them have been already in our web. You have used them, so it's a collection of examples. I will change this. This is the source version in LibreOffice version, so it's not the PDF. I'm sorry for that. And there is an exercise I will explain how to do. And files in POSIX is the pack of slides that we started yesterday to browse, and we will keep on now. So stop share. And now we will start with the just very briefly browsing the the pack of slide. Okay, was here, so I can do. Yesterday we already seen the syscalls number 1. I assume that you know what we have seen yesterday: header files to use, error messages, how to treat errors. It is very important. The global variable error number or error name, the P error, that is the basic call for the having diagnosis about last error occurred, how to use the manual. Manual is the official documentation of all POSIX commands and system calls. The concept of file, the file with a file descriptor. Remember, the file descriptor is the way in which we manage a file, a general file, the abstract concept of file that is used as a real file on disk device. We'll see a short example of that. Communication channel through the internet and so on. And remember that we have the 3 basic file descriptors that are always open as soon as the program, your process start, run by the shell: standard input, standard output, and standard error. Close disconnects all files. You know that open, to open a file. If the file is on disk, the alternative of creating is similar, but creating deletes an existing file with the same name if it exists on disk. Close is not always necessary. If it's a regular file on disk, you can forget to close, because exiting the process automatically closes all open files. But in general, remember to close, because there are several circumstances in which it is mandatory. You will see now, in particular, in inter-process communication. So close your files. How to read or to write. There's an example of copying standard input to standard output. Let's go on. The concept of caching, and this is another really important from the practical, from pragmatic and professional point of view concept, because if you need to be sure that your write operation is completed, and in particular for debugging purposes, you must flush the cache. And there are more than one system call, but this is a general system call, the simplest one, even if it is makes the system go a bit slower than normal. We skip, seek, not now, and probably we will not use in the exercise, but you must be aware of this, of the seeking. Seeking means move the pointer to the actual point in which you are writing, reading in a file, a sequential file in general. It is used in practice only in regular files on disk. Link, unlink, rename, and so on. I have to say something. They refer to regular files on disk. I have to tell you some more information about how a regular file is kept on the file system. Make directory, remove directory, change directory. They are the counterpart of commands in the shell. Directory structures and so on. So yes, please read and understand which is the content. So have the knowledge, the list of system calls that do that. Is to change the attributes and so on. This is really important, differently from the other one. We can add the knowledge of the existence of the previous system calls. DUP is the core for communication between process, dynamic communication. So to establish a channel for communicating and changing the channel during execution. So let me say again, yesterday we have seen what is the meaning of DUP, duplicate. This drawing shows that you have a file descriptor table that is in your the user area of your process with some file descriptors. File descriptor 0 points to a file table, so it's connected to a real file from the point of view of the kernel. In that case, if it's 0, probably it's standard input. And suppose we have 2 and connected to another file in the file table. This is the reference count, not name of file. Reference counter. That means there is one link pointing to this location. After you have issued the DUP2 is this one, you have asked it to establish an alias name for file descriptor 2. And the alias name for file descriptor 2 is number 1. Why number 1? Because it's free. It's blank here, is white instead of gray, just because in this example, this is not assigned. So the semantics of DUP is just to find the first non-assigned file descriptor and connect to the same that you have here as a parameter. So now there are 2 file descriptors pointing to the same file. We don't know which kind of file, may a socket, so for communicating in internet. But in any case, now you have 2 file descriptors. What is it for? We will see very soon. Oh, skip this. I think we are at the end. Well, that's theoretical information, but very important. No mutual exclusion is supported by the kernel while you use the read and write, differently from what we will see in the after for inter-process communication, in which the kernel also provides mutual exclusion in some cases. So if you want to operate several processes simultaneously work on the same file, with the regular file, I mean, on disk, on hard disk, or solid state disk, or memory mapped disk, In any case, no mutual exclusion is provided. So if you can write simultaneously in the same locations of the disk, and in this case, of course, what happens is data jamming. So there is also the possibility of locking, unlocking. I don't know if you have time to do some exercise on that, but I will try to propose you. So for now, we skip file locking and we go a bit further. This is an important point, just exactly for understanding the examples in the slide pack of the examples. It's a simple concept, but in C language, normally when you use a file, you have a type, predefined type, is defined in the headers of the standard headers. There is a file pointer. This is a pointer to stream. It's very similar to C++. And the concept is the same. You open a stream in this way. In C++, you call exactly stream. In C language, you call the file pointer. But it's not a file descriptor. Obviously, if you're using regular files, the two concepts are strictly related. But in this case, this value is just a pointer to file. It's a way of determining the link with the file, specify the file, but it's different from the file descriptor. Why this? Because at C language level, similar to C++ with C out and C in, you carry out also data conversion. So you can specify that if you're writing an integer, the integer is converted to the representation in binary format and so on, any kind. So there is data conversion. Data conversion is automatic in C++, and you must specify the conversion form in the printf or scanf in C language. So this is the file pointer in C language is something that supports data conversion differently from read and write system call read and writes that simply read and write streams of byte. You remember that the data type in the buffer that was written and read was just void, a void pointer, just bytes. So a string in C language, a stream is opened and closed and read and written, and so with such C, there are also POSIX primitives. The prefix is F, just to remember that is the file. They're similar to fprintf is exactly printf onto a file stream. There is similarity in this case, f open, f close, f read, right? They're similar to open, close, but they are, in jargon, they're called row. So in any case, the file is open in row format with no conversion. So if you write onto a file with a system called write, you just write a sequence of bytes. A file descriptor can be derived and file from by a string, by a file pointer, and on the contrary, A file pointer can be derived by the file descriptor, and we have, because obviously there is a one-to-one mapping, and these are the two system calls. So if you have the file pointer, you can get the file descriptor using file no, and if you have the file descriptor, you can use the fd open to get the stream. So you can use both versions in C language, and in some examples you must do that. And that's the reason why I have explained, because C system programmers, C language system programmers often decide to use one of the two philosophies, well, file pointer or file streams, or the file descriptor, basing on which is the main program, the interaction with the user and the algorithm. Okay, so this was in more details what you have seen yesterday, and because at the end there was the fork and exec that you already have used in several situations. So this is a sort of abstract of the yesterday's first part of the class. So if there are no questions, I will go into the file pack of slides, just to point out which are the concepts, the relevant concepts. Okay. So I go on. Okay. Okay, this is the slides regarding files. Can you see them?
Yes, yes,
okay.
We can see the slide.
Yes, we can see.
Okay. Files. We have already discussed that there are several kinds of files. A regular file is the file that usually are open and open on the hard disk, but you can open also other files we will see. Device files. Well, for device files, I think that it's interesting to see when you, well, I'll stop share. I forgot. I have to activate the shell. So this is the shell. Can you see the shell?
Yes, we can see the shell.
This is the shell. Yeah. Okay. If we go on the root directory, we see several other directories. And in particular, if you go into the dev directory, the directory trees is, even if it is not POSIX standard, is assumed as a de facto standard in all POSIX programming, and is reproduced also in some subsystems of Windows, and mainly the same in OS X, for example. If you just watch ls-l dev, has a lot of subdirectory or files. We don't know exactly. Some of them, for example, well, this is the hard disk. You see disk here, okay? And you see that those numbers, SDA, SDA1, SDA2, in this computer are the hard disks. And they have identified with two numbers. You will have this more detailed information in the real-time course. They are called major and minor number, and are number that identify the device driver inside the kernel. So you can open with the path name /dev/SDA, and in that case, you talk directly with device driver of the disk. It's a way that is everybody can do. In that case, you're accessing the disk in a raw mode as it was a stream of bytes of 100 or 500 gigabytes of bytes. So it's a very low level. If you open a regular file with a path name, it goes inside the tree, but you see that syntactically it is the same thing. You're not here in /dev, you go in /home or /renato, that's my home directory, / a file name. And so in that case, the system call knows that it has to use the file system method to access the hard disk. But in general, here, most part of devices, these are virtual devices, so in any case, are identified with the ID inside the kernel. That is conventionally a couple of numbers. In some cases, you can use, if you find the video, for example, this is a true driver that is similar file, the video for Linux, and you can open a stream of video coming from the camera and so on. So this is an example of, let me share again the, okay. Special or device is written here. That is, in any case, are file names interfacing at very low level. So in a sense, a regular file is an upper level of abstraction with respect to a special or device file, in the sense that is a call, it's a system call that uses all the software for managing the file system. You can have shared memory, you will see after, and pipe. And when we start using pipes, we go on. I have some information about that I want to transfer to you about how regular files are maintaining on the file system, because I think it's important. I want just to point out that here is the concept of volumes of files, so file systems. We will see next week just as additional information. I want to show you some remarkable special files. They're also called pseudo devices, very useful for debugging, and not only for debugging, but also for system programming. The null device Null device is a driver you normally used to discard everything is written into it. If you are debugging a program, a process in general, and the process generates a lot of data in output in the system window, in the interactive window, and you want just to run the program discarding all messages just to check if the other logics of the program are running and so on, you can redirect using the shell all standard output onto this file. It's a sort of black hole and writes and accepts everything and discards and nothing happens. Can be used also in input. In that case, you receive immediately an end of file. And so for debugging, connect together with the capabilities of the shell to redirect standard input, standard output, standard error, they are very useful. This similar to dev null in writing, so it's a black hole. But if you want to read, it generates a continuous endless stream of null characters. So 0 value bytes. So there are bytes with 0 written inside. Dev full is also able to generate this full error if you try to write. So you see that they're typical of for debugging your programs. And this is not only for debugging. That random is interesting because in many situations it produces bytes generated by the kernel, and it's the best possible algorithm for generating random numbers. They use also in cryptography, so has to do with the security and safety of the system. But in many situations, you can use the random numbers, and you are sure that they are very good random numbers or reliable random numbers. I think it was the last one. Yeah. Okay. So so far, it's the only thing we needed to know about files. I will also show you more about how files are the theoretical concept, but also in some cases can be used directly, or you must in any case be aware of and how regular files and regular files includes also directory and so on. Everything is written on the disk because the structure is in principle the same also in more modern and complex file systems like Windows file system, the so-called NTFS and other file systems. So the principles are absolutely the same. So I think probably there are no questions, but if you have questions, interrupt me. We will start now describing the inter-process communication that is called pipe, so that I will propose you an exercise in class, which is at the same time an assignment for the next week, and starting from this week, or the assignment will produce also the idea of having your feedback. So next week, next Tuesday, using a lottery, we will decide that one of you will show the result of having solved the assignment that you will start to discuss in the class. If it is okay, if there are no questions, I will have 5 minutes break, and so we will jump on into the pipe concept, okay? So no questions, pause recording, hope that Zoom does not collapse. 5 minutes break. Okay, we start again after a pause. We have just discussed answering a question about comments to the shell. Okay, POSIX Essential, pipes. We have a process, we have another process, and we want them to communicate. How can be done? Establishing a communication channel that is called pipe. As a matter of fact, pipes are like tubes, are bidirectional. So in general, it is possible to also to each pipe can be used in both directions, but is a common rule, even if not necessary, to use in just one, in only one direction, to avoid confusion and to avoid data jamming and so on. So pipes are used in if you have to write and read between two processes to exchange data in both directions, you, like in this case, you should use two pipes instead of one, even if one is sufficient in principle. Let me do the same scheme. So the theoretical scheme is this one, P1 and P2. They establish a pipe, and this pipe, this is a pipe. You use just like any other file, simply you have a system call different from open and close. Well, close is the same. Instead of opening a pipe, you use a system call that is called just pipe, just to distinguish between files, regular files, and pipe that is an internal virtual file. And so you can, in principle, you can read and write. And so you have two file descriptors. You have two file descriptors. When you call pipe, you have you get from the operating system two file descriptors, one for writing and one for reading. The problem is that in that case, the file descriptor for writing, for example, it is the same for both processes. So they put data inside this serial buffer, and it's difficult to distinguish which is the author, which is the producer, which is the consumer. So normal policy is even if the same pipe has the possibility of accepting data from both, if we want to have a bidirectional communication, so use this scheme. So generate two different pipes and use only one half of the pipe, one for writing and one for reading from both sides. So this is the reality. This is the theory. There are two kinds of pipes. Now we, for now in this class, we talk only on unnamed pipes. It's a producer-consumer model with the first in, first out channel. So it's a one-to-one communication. If you remember this possible schemes of communication, is not one-to-many, not many-to-many, is not a blackboard, it's just serial communication, send, receive, the simplest one. And it's synchronous, you will see the concept. A producer writes data into a pipe. This is a FIFO. And the consumer reads. So we are assuming that one writes and one reads. And so it's an implementation of the concept that I sketched in the beginning. So as a policy, please use the FIFO only in this sense, even if in theory it is possible that the consumer in its turn puts data here if he wants to become a producer, but don't do that. So it's similar to open, like open, in the sense that it gives you back a file descriptor. It gives you back two file descriptors. In a structure, in a vector, file descriptor 0, file descriptor 1. They are simply the name of that pipe for writing and for reading. The same order with like standard input, standard output, and standard error. Standard input is first, so file descriptor 0 for reading. So input and output. So from now on, please forget that both processes who know the pipe, who have the file descriptors, can simultaneously write and read using both file descriptors. So it's similar to a regular file. Create, file name, and so on, gives you back a file descriptor. Pipe, and usually the scheme is the same, so use the if to check if it's successful or not, because in also pipe gives you back value 0 or -1. -1 means error, so in this case if pipe and so on, write, read, do what you want, else p error. Possible scheme is this one. Let me just a bit smaller. How they are used. Well, this is the scheme. A father asks two file descriptors. Then it forks. This is the typical scheme. It can be used in any case, but this is the relevant situation and the one we will encounter in our course. Fork. From now on, two processes exists: the father process and the son. But this is the important thing: both know the file descriptors. FD means two file descriptors, one for reading, one for writing. Why? Because they are in the U area. And so both process, father and son, know the open files, and this is an open file. So for example, the father can write on FD1 and the son can read on FD0. So these are the two sites for accessing the pipe. They can do also the reverse. As I told you, please use one of them in alternative. Don't use simultaneously or the same algorithm for reading and writing on the same pipe, because otherwise, no, there's no data jamming, but you lose the order of the generated data on the buffer. So this is what in real case. So you close the unused end of pipe to be sure that you do not make mistake in any case and write or read what you didn't have to do. So for example, the writer, the producer, in that case the father, closes the file descriptor 0 for input. So from now on, there is no possibility for the father to read from the pipe. And the dual situation is in the son. It closes the file descriptor for writing, and so it is able only to read from that pipe. So you limit yourself to read or write or to use the pipe in one direction and not the two theoretical possible directions. This is what the shell does when you issue a command like this. When you pipe, this is the shell pipe. The shell pipe command that is parsed and executed by this shell. So it's instead of writing pipe or another name, is just a vertical bar, just to recall, but it uses pipe, uses the system called pipe. So the shell, when you write this, interprets this line and forks wait or proceed. Wait, in normal cases, if you say so, it waits. Proceed if you push command 1, command 2, ampersand. So the ampersand is the command to the shell that says, okay, go on and fork one more time. We will see after. We have already seen, but we will discuss also after. So in that case, the shell forks, generates a pipe. The pipe is necessary to make the two processes, executables, command 1 and command 2, to communicate each other. Remember that the pipe redirects the standard output into the standard input of the second. So the std out is redirected into std1. So it's not simply a way of making the two processes to run simultaneously, but it connects standard out to standard in. How? In this example, we'll see, and the same you will do inside your process. So generates a pipe. So the pipe is to make command 1 is a process, and command 2 to exchange data. You see here that there is an exec command 1 and an exec command 2. So the two processes are executed. Before executing them as a son and father of a fork, you ask a pipe, you shall ask a pipe. So with the file descriptor, two file descriptors for that pipe. So now there is a pipe in the middle generated by the shell. It forks, but both father and son, so the two processes, know that pipe because the file descriptors are in the user area. Correctly closes 1 and closes 0. What means close 1? 1 is standard out. And this is standard in. So from this moment, this line of code, the two processes, command 1 and command 2, do not have any more standard out, one of them, and standard in, the second. They cannot write, command 1 cannot write on standard out, and command 2 cannot read from standard in because it's been closed. But immediately after, there is a dupe. If you remember what the dupe does, it creates an alias of the FD of F. Wow. This is FD1, the file descriptor for writing, is duplicated, is a duplicate of standard out. So this is standard out. Because standard out was a number 1 and it has been, number 1 is reassigned to FD1. Because why this? Why that? Because you are sure, if you remember in the previous slide, because this is a blank line on the vector of file descriptors. And is the first blank line, and so it's occupied by the new file descriptor. And this happens absolutely the same thing. This is file descriptor 0 and is exactly assigned to 1, is a synonym, an alias for 1. In this case is the standard the in. So in that case, command 1 continues to run, writes on standard out, but standard out now as the meaning of standard out is exactly FD1. So it writes, the standard out is connected to the writing side of that pipe, and the opposite here. They start and they inherit from the user area that redefinition of standard in and standard out. They close the side of the pipe to be sure that nothing happened, nothing dangerous may happen. It is not mandatory. If you don't do that, everything continues to go on, but in any case, it's better to do. So that's the principle of redirection and the principle on how to use dynamically a pipe to establish a new connection between two processes, even if the processes thought to write on a specific channel previously. Hope it is clear. This is a chunk of code. that's named pipe are another concept. So I hope it is clear. In this case, in code, if pipeline, that is what I described above, forks, close, dup, close the pipes that are not useful, and exec command one. Command one now has the number one redefined as file descriptor pipe one, and the same in readme. This is the principle that is called of the unnamed. We have seen unnamed pipes so far. Oh, it's out of the slide. Unnamed pipes are the pipes that we have discussed so far. And they implement a one-to-one model of communication. Synchronous. Synchronous means that you cannot read from an empty pipe. So if you're attempting to read from an empty pipe, your process is blocked. You cannot write on a full pipe. Sometimes pipes become full and the process is blocked, just like reading and writing into files. So this is the general idea. And if it is clear, I will describe the assignment that you will start working on in this class, okay? Consider that you have examples of pipes in the slide pack that is called example. I will upload the PDF version instead of the ODP version.
Just a quick question, if I may. How big is a pipe? When does a pipe become full?
Well, there are parameters it's one of the many parameters for that you have when you install a new kernel. By default is something like some kilobytes. So there, you suppose that the two processes run at similar speeds. So a pipe should not become full. But you can increase the length of the pipe, the dimension of a pipe, by just trimming the kernel you need. If you have a special application, real-time application, which you are determining which is the best dimension of a pipe, you can decide to change. I think there are some kilobytes in general, some kilobytes.
Okay, interesting.
It's
Thanks.
transparent during execution because, of course, pipe full is not an error, just a reason for blocking a writer. In general, if you trim your operating system, your kernel, you prefer not to generate very big pipes because they occupy a lot of space in memory in kernel space, and you don't want to do that. So in general, kilobytes. I close this and I open the exercise. Zoom, okay. Okay, hope you read the exercise and we will start working on that, but just briefly, Can you see the, in any case, this is a file that is in our web, so you can read directly. Can you see the screen?
Yes, yes.
Okay.
You can see the file on the screen.
First point. Well, what you have to do now? Well, you don't have a lot of time because I was. In any case, just 10 minutes to discuss in groups. You have to, in the class, solve in your group writing a pseudocode, not writing the code, the final code. That is normal policy for writing, designing a program, in particular, in this case, a concurrent program. So use a pseudocode. That means it's syntax free, so you can write everything you want, but lines that recall the C language, and in particular the syntax of system calls with comments and so on, and use indenting just to design your algorithm. So please, all together, do that, just as the design all together in groups, in random groups as ever. Design the solution, and which is and when you're at home, one by one, solve and solve the problem in C code. And next week, so carry your solution. Next week we will decide one or two of you who have solved it, just to present, to show to everybody her solution. So, which is the, just in few words, you must create three processes. Three processes in the sense that one is the master, just like using threads. So one process forks 2 times to generate 2 children. I've called it first and second. So the algorithm, the master stays alive, interacts with you, asks for numbers, just a few numbers, for example, integer values, 5 integer values. So the numerical algorithm is not important. Puts in the order in which you have input, you have written data, stores in an array, sends the array to the first son, sends the values one by one. The first process, I call the first, puts in an array, sends the array to the second sorts the array, and prints out the number in a sorted series. So sorting algorithm is absolutely not important. So you can sort by hand or brute force, what you want. But the master is still alive, and after this process, waits for a sequence of other numbers, and the process continues indefinitely until you send a special data, decide you what is the command, so that the process decide to stop the two, to instruct the 2 first and second children to exit. The master process waits for the exiting of the 2 children and then exits in its turn. So that's the idea. With a model, with the 3 processes, with the master processor that controls, interacts with the user and controls the 2 children. For doing that, you need pipes, of course, because you need pipes to, at least one pipe to communicate the master with the first, and another pipe to make first communicated to second, and second can just print out the results or can send back data, the results to the master using a third pipe, as you like. So that's the idea. So all together now, try to, all together in groups, try to sketch the scheme of that and carry home the scheme and, until next Tuesday, code us, and we will decide to, one of you or two of you will present and discuss to everybody the solution. Just a last suggestion, please use exec, is written here, to run a child process. So don't put the code of the processes inside the master after forking. Exec a new process, so you can debug separately by running the process alone instead of having a chunk of code including everything. Hope it has been clear. I don't know, I'm not sure, but just try. I will also put in our web just a drawing with a scheme, a graphic scheme of the processes, but start working on that, okay? Now I stop and breakout rooms.